All right. Well, hey, happy Thursday. Today we're going to move on from just talking about general atomic structure, right? Like where we've been. We've been talking about specifically where electrons sit within the atom and the different kind of um, wave functions that they have and the different quantum numbers they have, like according to Pauli's exclusion principle. And so we're kind of we've talked a lot about the general idea of where the electrons are, um, which leaves two things to discuss. One is, well, what's going on in the nucleus? That's coming later. But the other is, well, what happens when we start putting atoms together? What happens when we start making molecules, like when we get to water, when we get to salt, when we get to like anything that's a combination of these? um, what are the consequences of these quantized states? What are the consequences of electrons having to be in different, having different quantum numbers? Um, you know, what's going on there? So that's what we're going to address today, or at least start today. We're going to talk about that kind of stuff. But before I go there, I want to turn it over to you guys. Any questions on the homework or anything else we've been talking about? Stuff that you'd like to look at? All right. Well, seeing it sounds kind of quiet and not seeing anything pop up, I think we're kind of good to go. All right. So let's just start here with different kinds of bonding. All right. So let's just start with bonding of atoms. So, from what you guys remember from chemistry or other science classes, what are the different ways that atoms can bond?
Covalently and ionically.
Okay, so those are the two major ones. There's the ionic and covalent. Um, there are also a couple of other bonding type things. There's hydrogen bonding. There's the van der Waals bonding, but these are the two main ones. And so we're going to talk a little bit about this, about why ionic bonding happens, why covalent bonding happens, what they are. Um, but we'll look at it from a physics standpoint, right? So let's actually start with ionic. All right. So what do you guys remember about ionic? What happens with ionic bonding?
I
I
know it's the weaker of the two, right?
yeah.
Okay. So it is a little bit weaker. That's for sure.
I think if I remember correctly that some atoms just take the electron.
Okay. So yeah, this is the one where electrons are basically traded. So what we're going to have is an electron from one atom is going to get traded to the other atom. It's just going to move from one to the other. And what that does is actually create two ions. And just to make sure that everybody's good with all of this stuff, because I know not everybody's like super strong on your chemistry. So an ion, this is going to be an atom um, that without neutral charge. So when we just talk about, when we've been talking about like the hydrogen atom, for example, um, its charge overall is 0. The electron has a charge of -1, right? Negative E. And then inside the nucleus is a proton, and it's got a charge of positive E. And so those add up to 0. So it's got neutral charge. All right. So regular old atoms have neutral charge. But if we give up an electron or we take on an electron, we're now going to be an ion because we don't have neutral charge anymore. Hence the name ionic bonding. So this happens when we actually create ions. All right, so let me just sort of give you a little schematic of what's going on. So let's say this is our nucleus, and we'll have a couple of rings of electrons here. But if we look at the outermost shell, that was called the valence shell. So let me just remind you about that. Is that valence? Don't care. It's either an A or an E. I'll just make it kind of look like both so you don't really know which one's which. So this is your valence shell. It's the outermost. And what happens here is that, let's say there's an electron that's out in the valence shell here. And then we've got another that's out here. And what will happen is this electron, if they get close enough, that electron is going to hop over and join the valence shell of the other atom. All right, so this first one, the one that I've got marked blue, since it gave up an electron, this now has a positive charge. Because it gave up one of its negatives. So let's just say, for the sake of it, that it had 12 protons and 12 electrons. It gives off one of the electrons. Now it's got 12 protons and 11 electrons, which means that it's got a charge of plus Q. All right, or sorry, plus E. Now this other one, by taking on an electron, has one more electron than it had before. So it's got one more electron than proton, and this one's got a negative charge. And so it's going to have a charge of negative E. All right, so the electron gets traded from one to the other. We now have different charges. So then why are they going to stick together? What makes ions stick together?
Isn't it the attraction of now the positive and negative charged full atom?
That's exactly it. Yeah, it's the electromagnetic charge. It's Coulomb. I mean, it's Coulomb's law, right? So it's the electricalness, the electromagneticness, that's making them stay together. All right. So now the question really should be, why does this happen? Why does one electron just all of a sudden decide to leave one of the atoms and go to the other? Well, you've probably seen enough physics and stuff that you could give me a reason, even though it's not explained.
Energy
One of them
level.
has a neutron. Yeah.
Okay, so Bradley, I think really it's the energy levels. The reason that this happens is because it causes a minimum energy state. All right, so that's what actually causes one of them to rob the other, is that the universe wants to go to minimum energy, and there's less energy necessary when they are close to each other. So here's kind of what's going on. If we were to look at, we'll make a little graph here. It actually goes negative, so let me do it this way. So this is going to be potential energy on our vertical. And on our horizontal is going to be distance. So the distance between them. And when they start getting close, right, there is going to be a potential energy ness to them. And what this graph ends up looking like is something like this. So that when they're really, really far away, the potential energy between the two is basically zero, right? There's no One of them doesn't notice the other or anything like that. And as they get closer, there is going to be some potential energy because of the interaction between the electrons themselves, right? Like think about it, as these two things are coming together, it's the electrons that are really reacting with each other before the nuclei. And what do electrons want to do? Well, of course, they want to repel each other. But anyway, you get something that looks a little bit like this. So think about what the universe wants. The universe wants to minimize the energy. Okay, well, obviously we want to get to that. But if you actually look at the forces here and the attractive interaction between them that comes from the 1/r², if you just have the one atom or separate atoms, you don't get quite this graph. You get one that's a little bit offset, and it would look more like that. But notice how this energy is so much lower than the other one. And so what will happen is as they're coming together, the electron feels it. It recognizes that it can actually minimize its energy by hopping to the other one. And so that's what actually drives ionic bonds. All right, so it's a minimization of energy, just like always. Okay, so we then have basically a stronger state because it's lower energy. But you guys may remember from chemistry that ionic bonds are actually pretty easily broken. In fact, Jacob, when I first talked about this, remember Jacob said something like, it's the weaker of the bonds. And weaker just means you need less energy to cause it to break apart, right? Like if they're bonded, I can pull them apart. Like suppose it was just like two things that were put together like Legos. I can pull them apart. I just have to give enough energy. I have to apply enough force to make it happen. And the same thing can occur here with your ionic bonds. But that energy that keeps them together is what we call binding energy. Write that down. All right, so binding energy, this is sort of that extra energy dip that we get from bringing these together. Right, so for example, I just know this one because this is kind of a classic. So NaCl, sodium chloride, also known as salt. Okay, so just good old salt that you put on your French fries is sodium chloride. And sodium chloride, this has a binding energy of 5.7 electron volts. And that's at when they're at this special separation, the one that brings us to the dip. All right, so I don't remember what the separation is for sodium chloride, but there's going to be a specific distance that they want to be in. If they get closer, they start repelling each other. Right? If they get further, again, they're getting brought back together, which seems kind of weird. I know it's like, how can it repel one way and then get drawn together in another? But it's really just because of the interactions between the electrons and the nuclei, and those things get a little bit different. But anyway, so this 5.7 electron volts, that's your minimum here. But the binding energy isn't this 5.7 electron volts. We actually have to take away from it what we would have if they were just separate. if you just had the sodium and the chloride atoms just by themselves. So it's actually a difference in those two. And if I recall correctly, this is like 1.5, like 3 or something like that. I'm going to go ahead and call it 1.53 electron volts. But I know that this ends up rounding to about 4.2 electron volts. And on our graph, that's this distance. It's the distance from the low spot here compared to the low spot if they were separate. All right, so that's actually how much energy you would have to supply to be able to break these two apart, to what we call dissociate those things into two neutral atoms, basically bring this electron back. Anyway, so this is the idea behind ionic bonds, is that the universe is just trying to minimize energy and get these guys together. All right, so there's ionic. So then what does covalent do? Do you remember what covalent does?
The electrons get shared back and forth.
Okay, so this one, then we just say that the electrons are shared. So we either trade them or we share them. So let me kind of erase this. All right, so what's going on in this picture? And what's beautiful is I can use hydrogens to do this, because hydrogens share a covalent bond. So here's hydrogen number 1. We got our nucleus and we've got our electron, and then here's hydrogen number 2 with its nucleus and its electron. And as these guys come together, what ends up happening is you sort of get the 2 nuclei, and then it sort of forms a, I'm going to make it like a little peanutty shape, but obviously there's no orbit or anything. But that now holds the 2 electrons as if they were in the first shell for N, or for the hydrogen number 1. But they're also like they're in the first shell for hydrogen number 2. So it's almost like these two things are sharing the same outer shell. So they're sharing these electrons. Okay, so this is the idea behind a covalent bond. Now, it can happen with other things as well. Hydrogen is just a really nice one to kind of illustrate. All right, so why does this happen?
Because it's better for the valence shells to be filled. It's better for the energy level for it to be full than not.
All right, so yeah, it comes back to energy again, right? Coming together actually minimizes our energy. So when they're being shared, we're in a lower energy state. Okay, let me show you why. Let me show you why. All right, so let's just say we've got, you've got all these electrons in your first one. So maybe let's go from something from hydrogen to something that's got more stuff in it. All right, but you got all these electrons, and by Pauli's exclusion principle, we know that all those electrons have to be in different quantum states, right? So let's just think about it this way. Suppose that maybe in the outermost shell, we've got like all but one. So we've got all of our states but one. So let's go to something bigger. Let's say that we're in one of those where there are 8 states, 8 possible states on the outside. And so let's say that 7 of the 8 are filled for atom number 1. And then for atom number 2, let's say the same thing. Okay, so atom 1 and atom 2 both have 7 of the 8 states possible for the electrons filled. Now, as these start getting closer to each other, the wave functions for the electrons in each of these start interacting. Right, like, I mean, obviously the wave functions tend to go forever, but as we go really far out, they get really, really low. So we're really only looking at the wave function, you know, nearby. Like, think about what we saw for the wave function in the hydrogen. I don't know if you remember it. It looked something like that, right? Where that was A. Now, obviously, this is going to be different because it's not hydrogen, but it would have something that looks kind of like that. Now, here is the wave function for one of the electrons over here. And let's say we've got a wave function for one of the other electrons. And so that's something like that, right? So it looks similar, just in reverse. At this point, they're barely interacting. These things are both so low that they don't really recognize each other. But imagine that this moves in closer, and now it's something like that. These wave functions are on top of each other. They're definitely running into issues. And Pauli's exclusion principle kicks in. So think about what's going on now. Now we basically have 14 electrons, but we don't have 14 spots. We only had 8 spots. So what's going to happen is some of these are going to have to bump up to the next shell. We're going to have to increase our energy. All right, well, the universe doesn't want that, right? So what would be better is if we could just take like one of these guys and fill it into this 8th slot. And at the same time, have one of these guys and come over and fill that 8th slot. So that the only ones that are really interacting are this one electron. Well, that's the one that now is being shared. And that's what's creating our covalent bond. So the reason covalent bonds happen is totally the exclusion principle. That we can't have electrons sharing the same state. And so they kind of shuffle each other so that they're not doing that. So what you would actually see, if we were going to talk about, remember the electron cloud and where the electron might be, like when they're separate, the electron cloud has that nice big ring at the Bohr's radius. And then there are a few here and out, but it's really kind of spread out. Well, when they come together, this electron cloud deforms so that it's not really a circle anymore. It's more of like a bulge, and then you see the same thing over here. They get pushed away. So when you actually do the wave function calculation using the formula, so if you go back and use, I lost the name, Schrodinger, Schrodinger's equation. When you use Schrodinger's equation for when they're together, it changes the distribution, it changes the wave function for the electrons that are not shared. And it also changes those for the ones that are shared, but you get kind of this weird hybrid wave function, I guess, for lack of a better name. But anyway, so that's what's going on with covalent, and it's the same deal though. It's a minimization of energy. So if you were to look at the energy graph, you're going to minimize it when you have covalent bonds. Now, covalent bonds are much stronger. they tend to have a much larger binding energy. And that's what Jacob was alluding to earlier when he was talking about how the ionic are not as strong. But there you go. All right, so ionic electrons are traded, covalent electrons are shared. Okay, now, what happens when we start bringing lots of things together? All right, so what if we're going to go from just having two atoms that are coming together to a whole big string of atoms coming together? All right, well, in that case, what we want to do is sort of look at the energy graphs of these specific molecules or atoms and start putting more and more and more of them together. So let's just say we've got two hydrogens together. Each of those hydrogens is going to have an electron. And so the one would maybe have an energy graph that looks like this. And then when we put the second one together with it, its energy is going to look a little bit different because they can't be identical. Pauli's exclusion principle. They're going to have to take on different states, and each of the different states is going to cause a little bit of a different energy deal. So there would be like two together. All right, well, put in a third, put in a fourth, put in a fifth, put in a sixth, and think about what's going to happen. All right, so at each one of these levels, we can only hold so many electrons, and so there's going to have to be now another electron. But also within here, we can start getting a little bit of spread. So here's maybe the third one, and then there's the fourth one, and the fifth one, right? And then there's going to be another level up somewhere here, right? So each of these is a different electron in our group. But as we start filling these in, start noticing that these quit looking like lines and they start looking more like thick bands. So if we're at just some distance away, so let's just pick a distance and go here, right? So here's our radius. What we're going to see if we were just to look at energy at that distance, you would see basically a filled in band that corresponded to these guys. And then the next one, we would see a filled in band, like all kinds of different layers, but it's got to fill in. It starts looking like a band and another one, and so on and so forth. So when we start putting a whole bunch of molecules together, we start getting energy bands. Instead of just one energy amount, we start seeing bands of these. Now, they are all unique though. If you zoomed in, you would see the individual lines. But there are so many of them that all those individual lines start looking like they're thick. All right. So what we end up getting then, if you were to look at this, so here's a graph of energy, and you're going to see bands. And so these are acceptable energies for the electrons. All right, so then there's going to be another one up here maybe, and then another one up here. And the thickness of those bands really just depends upon which molecules we're putting together and so on. So imagine just one crystal, one salt crystal. Okay, just one salt crystal, really, really tiny. But think about how many molecules it has in it.
A lot.
Right? Just like, yeah, a crap ton, right? I mean, we're talking huge orders of magnitude. And so if every one of those has a corresponding little line, and we're going to zoom in, I mean, you'd have so many that you couldn't even tell. All right, now it's this nature of the energy bands that leads to why some materials are conductors, why some of them are insulators, why some of them are what we call semiconductors, and so on. So let's talk a little bit about
Is magnetized part of that too?
in terms like is magnetism affected by this?
Yeah.
Yes, but it's a little bit different of a deal, because what we're going to be looking at when we talk about things being insulators or conductors, we're going to be looking at the ability of electrons to move. And for electrons to move, they have to go to a different energy state. Where with magnetism, it's not really as much an energy state, but it's kind of similarly related. All right, so let's start here with insulators. So an insulator, this is an object or a material that doesn't really allow movement of charge. All right, so that's what we're going to mean when we say insulator. This isn't a temperature insulator. It's different than when we were talking about thermal insulators. This is an electrical insulator, so it's not going to allow movement of charge. All right, now how these play out. What happens with insulators is, suppose that we've got the graph of our bands. Change colors here. But maybe like, here's the first band, and then we'll put in a second band, and we'll put in a third band. Okay, so here's our bands. What we see with insulators is that the energy level of the insulator at its just sort of its standard base level is somewhere between the bands. And it's usually closer to one of the lower bands. So basically, here's what happens. Your electrons start taking in the energies in the first band. They start taking in the energies of the second band, right? So they're all full. Now, for an electron to move, basically for a charge to happen, we need one of these electrons to be able to pop up to the next band. And right now, that electron has the energy where I've marked it here with the dashed line E, but it's a pretty far distance. It's a pretty big gap. So that's going to require quite a bit for that electron to be able to jump up to this next band and be able to move around. This band, the way I've got this drawn, this would be the conduction band, because that's where electrons go to move around. And then the other one, this is the valence band. Because it's the outermost, it's the highest energy one. And again, so for insulators, there's a big jump between the energy level of the atom, the electrons in the atom, the outermost electrons, I should say, and the conduction band. So that's what makes something a good insulator. Obviously, if just sort of the baseline energy was up higher, this one then is not going to be as good of an insulator because it doesn't require nearly as much of a jump. And you've probably seen that or may remember that from E&M, that different things behave differently as insulators. Some are better than others. And this is exactly why. It's all about where those allowable energy bands are compared to the energy, just the standard baseline energy of whatever that material is. All right, so that's what makes something a good insulator. So let's talk about conductors. So things are really good conductors if it doesn't require much energy for these electrons to move. All right, so for a conductor, this is something that has easy movement of charge. Okay, so it doesn't actually take much for that to happen. Now, here's what we see with a conductor. So I'll do the same thing. Let me draw some bands in here. So there's the first band. Here's the second band. Maybe here's a third band. Now, for a conductor, what ends up happening with our standard energy level is that standard energy level is somewhere inside of the band. Now, remember what this band is made up of. It's made up of a whole bunch of energy values that are really close together. And so in this situation, it's super easy for electrons to move up. They don't have to jump all the way to this next band. They just need to jump up to one of the other levels here. And those are going to require very, very small amounts of energy. So it's very easy for that to happen. And then once these things are up and free, now we've got holes. Those holes can get filled in by things on the side. These want to move either direction. And the next thing you know, we've got movement of charge, which means we've got electricity flowing, right? And we've got conductors. So really good conductors, things like copper, gold, those are such that, again, kind of their baseline energy levels are smack dab in these energy bands and allow really easy bumping up of electrons into these higher states, but then allow them to move. All right, so there are insulators and conductors. But then there are what we call semiconductors. And I'm sure you've heard that term as well. But let's talk about semiconductors here. Okay, so a semiconductor, this isn't exactly a conductor. It's not that the energy level is right in the middle of a band, but it's better than an insulator. It does conduct electricity. It does allow movement of charge, better than an insulator. And so I guess what I would say here for a semiconductor is maybe it's got moderate movement of charge. And these are ones where really what's going on is that the gap between bands is small, right? So think about when I showed a conductor, we had this band and then say another band. Let's say that this was the one that we could jump to. It had a pretty big difference in energies. For a semiconductor, what you're going to see, so maybe here's our lower band. Our higher band isn't separated by much. So we're in the same kind of situation as with insulators, where energy level, let's just say, is like right at the top of this lower band. It doesn't require as much for it to bump on up. All right. So semiconductors really do behave a lot like insulators, or the setup is the same as insulators. It's just that jump is much smaller, which means it's much more likely to happen, which means we can make the charge occur more frequently.
I have a question for you.
Yeah, go for it, Bradley.
Is water a conductor or a semiconductor?
Is water a conductor or a semiconductor? Ooh, that's a good question. I would say that it's a conductor. I believe that it's a conductor because charge really does like to flow through water. What made you think that it might be a semiconductor?
So the only reason why I thought maybe semiconductor is because when I think of a normal conductor, I usually typically think of metals.
Uh-huh.
And water, when I think of it conducting electricity, is usually in a liquid state. So I didn't know if that played a role or not.
I don't know technically where we would put water in the, like, if we're going to classify it as one of them. I don't know technically where they put it. But I'm inclined to think that it's a conductor just because I know how easily charge flows through it. Although I don't know how well charge flows through it when it's solid.
My guess is it's not as well, but I don't
Oh.
want to test it.
Yeah, yeah. And it makes sense that it's not. Honestly, right? Like, think about what happens when we go from liquid to solid.
There's less energy in the solid form.
Okay, so there's already less energy. And to think about the bonding, right? Now that we get to crystalline structure, we're going to have more bonding between the molecules themselves. And that bonding is going to make it so that there are fewer free electrons, right? More, the electrons are now being used more to create all the bonds between all the molecules. So there aren't as many that are available just to do their thing. So it would make sense that when you go from like liquid water to solid water, that you'd have a decrease in conductivity. Which makes me think that that might even be the case with things like the metals, right? Like you're saying, you know, when you think about good conductors, you think of metals. For me, I always go to copper, right? Because like think about how many wires in our everything are made out of copper because it's a good conductor. But that makes me wonder, well, what if you had liquid copper?
I don't know. I was just thinking about that too. Like, I don't know if it would work as well or better. I have no idea.
Yeah. Yeah, and there you start getting in such higher energies that maybe a lot of those free electrons start like escaping even from the copper. So I honestly don't know. It is not my forte of physics, obviously. So I don't know off the top of my head.
It could be the facts of ionic versus covalent bonding, in which phase it is in. It would dictate how much better or worse of a conductor the substance may be.
Mhm.
It's like what we just said with water, that's a covalent bonded molecule. We pretty much agreed that it would be less conductive in the solid state, but copper, it's solid, ionically bonds with itself. I don't know if that has something to do with it or not.
Yeah, I honestly don't know. That'd be a good question to ask Sean. See what he says. That's a good question. Yeah, I'm not really sure. But I would definitely put water in the conductor realm. I'm going to guess that's where it is.
I think it needs to have a It needs to be salted or something first. It needs to be like, have ions introduced to it. Otherwise, it acts as an insulator.
So if it was deionized water.
Yeah, apparently that's a very good insulator from what I remember reading.
I could buy that. I could definitely buy that.
Yeah, I could buy that too.
Because here's what happens when you start putting impurities in. Let me draw you another picture here. So let me just erase this stuff and come around the side. All right. So suppose that we're in a conductor world or a insulator world or semiconductor world where this one's filled. Okay, so this is the valence band that's completely filled. And then we've got a conduction band above it. Now I'm not going to shade it in because I want to show that it's it's empty. All right. So here's our convalence band, our valence band, and our conductor band. Now you start putting impurities in there. You start putting in things that have sort of extra electrons that are free to give. Like, Jacob was saying, if you got like salts in the water or other kind of minerals, that's going to put electrons at higher levels. It tends to put electrons at higher levels, which then can start hopping up. So this is going to be an impurity of some type. Now, sometimes this is done on purpose. We call that doping.
That's a great word.
Yeah, right. So this is intentional introduction of impurities. And again, this is done on purpose because now these impurities, the electrons from the impurities, are much closer to that covalent or conduction band. And now these things can pop up and start creating the charge. All right. So that's what's going to happen clearly with water as we start putting in other stuff that is now freer to move around. The other thing that can happen actually, if you have impurities, you can create another kind of impurity, which basically creates, instead of creating or putting in electrons that are at a higher state, it can actually create other states that are in between. Okay, so here again is our picture of the filled valence band and then our conduction band. But the other thing it can do, instead of just putting in an impurity and making it so that there are electrons that are up higher, it can also kind of put in another level here. We call this an acceptor level. And what this allows now is an electron that's in your valence band to hop up here, which then creates holes that allow electrons to start moving around, right? So these things can now hop up to this level. So it's really, there are two different ways that impurities assist in the conduction of electricity. But I'm sure you've heard of semiconductors. I mean, they are used a lot in electronics. right? We have all kinds of semiconductors and things like diodes, for example. Do you know LEDs, right? The light emitting diodes. Diodes are designed to be semiconductors. And in fact, they're kind of funky because they only allow flow one way. Did you guys talk much about diodes in E&M?
Not that I remember.
Yeah, I don't remember going over them in circuitry.
Okay. But anyway, so diodes are created in such a way that it only allows flow in one direction. The current can only go in one way. That's not true. The current can go the other way, but it ends up being much smaller in the one direction than the other direction. Well, anyway, so semiconductors are used to create those kinds of things.
What about superconductors?
Okay, so what do you think a superconductor does?
I mean, I would assume it just does what a conductor does very well, but I mean, at the same time, like I've seen some like videos of the sort of things that they can do, and it's a lot different from what you would expect of like a conductor like copper, you know? Like being able to pin magnets like in the air.
All right, so superconductors. So like think about the one with the magnet kind of idea. What it ends up doing, obviously, is creating a very strong magnetic field. What makes magnetic fields?
Current.
Okay, so it's tied to current, right? So motion of electric fields creates magnetic fields. So when we have a conductor, we are creating current because we're causing these things to move from, we're getting electrons so that they're free to move. So a superconductor, what it's going to do is it's going to allow lots of motion of charge, which then ends up creating your magnetic fields that makes it so that you can like levitate things, right? And so that's really what's going on with the superconductor, is that it is a conductor. It's just one that allows a large amount of charge. So like if we come back to this picture, well, that's a semiconductor. Let's come back into the conductor picture. This is such that these bands, or the lines within the band, are so close and everything that stuff is just constantly moving back and forth, and it just allows, like it says, it's a superconductor, so it's doing conduction, but just lots of it. All right, so in terms of these allowed energies, and you know how I kept drawing like this line of here's what the energy is, I would be remiss if I didn't give you the name of that and talk about this a little bit. This is what we call the Fermi energy. We usually use E with a capital F subscript on it. All right, and the way Fermi energy works is this. Okay, so at 0 Kelvin, and I know, just because we can never quite reach 0 Kelvin, right? But at 0 Kelvin, this is the highest energy level filled by an electron. We'll put in the atom. All right, so let's just think about this. So we're going to build an atom, and we're going to be at 0 Kelvin, so we don't have to worry about the non-quantum energy, right? As we start warming it up, we have other energies. We're giving it more kinetic energy and everything, but I just want to talk about what does the energy do to its quantumness? So think about what we're doing. We just start filling in, right? So here's the first electron and it goes at this energy level. And then the next electron goes at this one, and then the next one goes to this one, and so on, right? And so we just keep filling them in until eventually the last electron gets into the last state and we finish it off, right? And so this would be your Fermi energy. Gosh, I cannot draw today. Let's try that again. That's better. All right, so that's the, if all we're doing is we're filling in the allowed slots with our electrons, we're going to reach our Fermi energy. So every time that I drew that sort of like dashed line, I was talking about the Fermi energy. Now, as I heat it up, those things are going to get more excited. And so they're going to kind of move a little bit higher up on the graph. But that's what this would be for just plain old zero Kelvin. All right, now, as temperature increases, the Fermi energy, it doesn't increase, but the graph of, say, the probability, we're going to put here the probability of filling this energy level. And then this is going to be, oh, no, I want this energy. Here's what it would look like at 0 Kelvin. At 0 Kelvin, here's our Fermi energy. And on this graph, there's a probability of 1. This is 0. We would see a graph that looks like this. Every energy state, and remember, this isn't continuous, it is discrete, right? They're just specific energies. But every energy less than the Fermi energy is going to be 100% guaranteed that that is filled with one of the electrons. And everything greater than the Fermi energy is not going to be filled. So that's 0. But in reality, when we're not at 0, so this is 0 Kelvin, let's say that we increase the temperature a bit. All right, well, at the Fermi energy, what's kind of interesting here is that the Fermi energy always has a 1/2 probability no matter what the temperature is. So you got a 50-50 shot that the Fermi energy is filled regardless of your temperature. But as you increase temperature, what'll happen is your graph will do more like this. And if you think about it, it should totally make sense. These lower energy levels are now less likely to be filled. There's a lower probability. And the higher energy levels now have a greater probability than 0. That's because some of these are going to get excited and pop on over.
And that's because we increased temperature, yeah?
Yeah, so we're increasing temperature. So if I gave you another one here, let's do another that does something like that. What I can tell you is that the green temp, that's going to be lower than the red temperature. Because I'm staying full, I'm guaranteeing more of those lower energy levels because I'm not introducing as much energy from the temperature. Right, so as we stray from 0 Kelvin, when you're really low temperature, it's going to still look pretty boxy. It's just going to be rounded a bit. But as that temperature gets bigger and bigger and bigger, it becomes much more smooth and looks way less boxy. Anyway, so just so when you're reading something and you come across Fermi energy, that's what we're talking about.
Is this the same Fermi that did the Fermi paradox?
It is the same Fermi who Fermi Labs is named after. Yep. I think that was Enrico Fermi, I think is his first name. For some reason, that's what is coming to mind. But yeah, so that is the Fermi energy. So then here's what's kind of wild. You remember all that stuff we did back in thermodynamics when we were talking about like the specific heats, and there was like the specific heat of volume, the C sub V, and all that stuff where we talked about the molecules, the energies that were in them from uh, from the rotations, the spinning, from the like vibrating backwards and forwards. All of that, all of those formulas come directly from looking at energy in this quantized world. Like it's another place where everything just fits. And so when you look at this macroscopically and relate it back to this quantum stuff, it still totally follows. So just more evidence that this idea of quantized energy, of step energy, is right. It definitely feels like it should work this way. All right, so that's a little bit more now about what happens when we stick things together. Basically, we're going from individual bands or individual energy lines to bands of acceptable energies. And in that case, it starts to look kind of continuous. Obviously, it gets more continuous as we introduce more molecules. But just so you guys know, like, what is Avogadro's number? That's 10 to the 23rd, right? 6.02 times 10 to the 23rd.
Yeah.
Okay. And that's how many molecules are in 1 mole of a material. And a mole is not really that much, right? Like what's a mole of water weigh? What's the mass of a mole of water? Anybody remember?
I think it's pretty much exactly 1 kilogram. Like,
Okay.
I thought that's how it was designed to be.
Okay, and I'll take your word for it. That sounds good enough to me. So just think about that: 1 kilogram of water. And if you're not super down with the metric, right, that's what, 2.2 pounds of water, which is not very much.
No,
Okay.
I'm wrong. It's about the density. It's 18. It's 18 grams per mole. Sorry about that.
18 grams. Okay, so even smaller. Oh my gosh, so 18 grams. So think about 18 grams of water, little tiny amount, and that's going to have 10 to the 23rd molecules. Think about how many electrons are in each molecule. And all these electrons are starting to interact with each other and all that. Think of all those lines. And yeah, I mean, they're individual lines, but the next thing you know, it looks solid, right? But that was kind of the whole point of quantum, like why this quantum idea still works, even in our big macroscopic world. It's because when we start getting to this so many things, those lines get so close together that it doesn't look like they are little steps. Those steps get so close together that it looks like it's a ramp, right? And this is just another case of that.
Oh, so that's probably why they thought it was continuous at first.
Sure. Because
I
mean, think about these energy levels we're talking about, right? We're talking about electron volts, right? Like when we're talking about the go back to the Bohr's thing, right? And we're looking at electron volts, and it's 1 over n squared times 13.6 electron volts. So even at its worst, 13.6 electron volts. So an electron volt is 10 to the minus 19 joules. 10 to the minus 19. Okay, so we just multiplied that by 13.6. Okay, yay, now we're on 10 to the minus 18. That is such a small amount of energy. Think about the energies that you guys calculated in the lab in the first quarter. When you're just talking about, the kinetic energy of a ball flying through the air. Those were not super high, right? They weren't huge numbers of joules, but they were joules. So even if we're just talking about 1 joule, you're 10 to the 17th times as big as these jumps, as these energy jumps in the atom. They may as well be continuous at that point, right? So it's just one of those things that because of the size disparity, in our world, in our big macroscopic world, no, we don't see it at all. Don't even notice it, right? But when we start actually breaking down and going down to the atomic level, to nuclear distances, that now it matters. And so we're going to start seeing it. So that's why this whole quantum thing didn't really come about until physicists got to a point where they could look at this macroscopic world or a microscopic world. And then they started realizing that, ooh, maybe it's not actually continuous because of all the things that we've talked about. How if energy actually is continuous, you don't get things like the photoelectric effect doing what it does. You would have electrons that are, slowly degrading into the nucleus. You're not getting discrete lines of light radiating off of these objects, right? So it's just one of those things that at the time, sure, it was continuous, everything's great. But as technology got to the point where we could start investigating these smaller things, started going, no, that doesn't really work so well. Here comes the idea of let's make it so we've got little finite packets of energy that fixed all that stuff. And because those packets are so small that when we extend it out, you just go, okay. So it's going to look continuous at these big levels, and sure, it fits. Anyway.
I have a quick question for you.
Yeah, go for it.
So like things like helium gas, how do things that are, like full valence, everything's all copacetic in the nucleus, how do they interact with each other?
So you mean like when you get like 2 heliums together?
Exactly, yeah.
I don't know. I'm not even going to make a guess because I'm not certain. It's obviously not ionic, right? And it's not covalent because there isn't anything to share. So it's probably more like a van der Waals kind of thing, but I'm not really sure. I'll look into it, but I don't know the answer right now. All right, well, I think this is a good place to stop. So we're going to go ahead and call it for today. So just going to remind you to keep working on the homework. I will get a chapter 8. I think we're at somewhere homework out for you here soon. But other than that, have an awesome weekend, and I will see you all Tuesday.